what could it be? What could it be? And it's easy to think that it would be to understand what is common to a tree, an apple, an animal, what they have in common. A lion, a tree, and a mountain. What they have in common, you know? So, numbers. Numbers. The first, and there is record. This is the oldest record of marks on bones, where you could see that 30,000 years ago there is a famous Lemaitre bone with 29 marks. It's not clear if it's 29 because there is one at the beginning that it's not clear if it's there or not, and you know. So and this this by the way is associated with menstrual cycle. Yeah, menstrual cycle with the moon calendar. With the moon calendar is not clear, of course, but it could be associated with that. There are also other famous bones. One is the Wolf one in the Czech Republic, 30,000 years old, and another one is Shango bone, which is even more famous because in the first one, in the first bone, there are only these marks. In the other bones, they are, you know, not just the marks, but they're groups of marks. Yeah, so there was already some calculus there. Some calculus was there. Okay, so this is the very beginning. Now, the pre-Socratic philosophers, they already had these concepts as substance, number, power, infinity, movement, being, atom, space, time. They had already this concept. And starting from 600 years before our era, and you know that mathesis for Plato, he called ta mathemata. This was the knowledge of all. This was all knowledge that could be learned and that could be taught. This was the definition of ta mathemata in Plato. So that mathematics is the origin of knowledge, we can say. It was called in this way. You know, this was Plato 200 years after the first pre-Socratic philosophers. Yeah. Well, here is a reference, very nice reference that I had to translate from German to Catalan. The historians in science, they asked me for help in these things, and I learned a lot from these books. In the Pythagoras school, we know that all things are numbers. For Galileo, the book of nature is written in mathematical language. Kant went further, maybe not in the mathematical thing, even if these philosophers, all of them consider this ta mathemata and all this history of knowledge, yeah, is there in Heidegger, Kant, and all these philosophers. And for Kant, the key point is that, you know, he said it in this way. This is translated from German. The problem is to make intelligible the idea itself that the universe is intelligible. Albert Einstein, he shared this opinion and he copied the same sentence. This is a different way of saying exactly the same. You know, that the eternal mystery of the world is its comprehensibility. Why is the universe so understandable for us? Why? It's a mystery, and a real mystery. Yeah? And well, they say understand. Yeah, maybe we say understand is not the word because understand is, you know, is too much. But to describe, we can describe the world in terms of very, or more or less simple mathematics, as we will see. Eugene Wigner, he said that it was irrational, yeah, that the mathematics was so effective. Yeah? Irrational effectiveness of mathematics in all natural sciences. Okay, now let's go. This is an example. Yeah? After these big concepts, now a very simple example of what the use of mathematics in cosmology. Yeah? And for this we go back to Eratosthenes and his famous experiment, not experiment, calculation, yeah? 226 years before Christ. Yeah? So imagine, yeah? 276 years before Christ. He just looking at, well, maybe all of you know about that, yeah? Looking of the sun rays falling on Earth, knowing from Alexandria library that at some point these rays were vertical, yeah, vertical. In Siena, Siena is Aswan, yeah, is the modern Aswan where this big water reservoir was built, yeah, and paying, yeah, because this is what he did, pay, yeah, these leaders of caravans, yeah, traveling from Alexandria to Aswan. He paid them in order to count the distance, to measure the distance between the two places, and just then, you know, with this very simple formula, and of course, looking at the same instant when he know from these manuscripts that in Aswan these rays were vertical, what was the angle that they formed in Alexandria, and knowing also that the Nile is more or less follows closely from south to north one meridian of the Earth, and with the hypothesis, because you have to do some hypothesis, that as the celestial bodies that he could see, they were round. Yeah, you make the, well, if these celestial bodies are round, it's most probable that ours is also round. This is an hypothesis. And with all that, and in this simple line, he calculated the radius or the circumference of the Earth in what is one of the most famous findings in science nowadays. You know, in these classifications, then this category, they say the 10 most famous, this always appears there, yeah, because this is science. You know, this is science. Every time you explain this to young people, they are astonished, you know, of course. Yeah, with this simple means you calculate this big thing, the radius of the Earth. You know, this in the year of mathematics, this was in many places, in many schools. Yeah, this was done, and also, you know, of course, you have to introduce these corrections here. If you are not in a maximal circle of the Earth, you have to introduce corrections. You know, but okay, this is just to remind you of the use of mathematics. This is astonishing. This is really astonishing. Okay, now let's jump to Galileo. Galileo is considered to be the father of modern science by Einstein. And Stephen Hawking also said Galileo is probably more than anybody else the real responsible of the birth of modern science. And really, Galileo had an important knowledge of what are now called the Newtonian mechanics. Yeah, it was already in Galileo, these laws of movement. Yeah, and you know, the Galilean group still is called, yeah, you know, the invariance group, that physics is invariant by uniform movement. Yeah, if the laws of physics are valid here and you have another system in uniform movement, the laws of physics will be valid there, and this is the Galilean invariance. And by the way, I did my PhD thesis on this in comparison with relativistic invariance, yeah, with Poincare group and this kind of things, and at the level of quantum field theories. Okay, now I want to stress this point now, because we are dealing with mathematics and universe, yeah, and what is the difference? What did Newton do more than Galileo? Newton did an impressive thing, yeah, which is the introduction, yeah, of infinitesimal calculus. What Galileo already said that the book of nature was written in mathematical language because by experience, he was experiences with inclined planes and in the Pisa Tower, and from his experience, he could see that there were mathematical relations governing the world, but he did not have the means to express them properly. He did not have the means. And Newton with the infinitesimal calculus gave a powerful tool, an impressively powerful tool, at the same time as Leibniz, of course, they say that Leibniz copied from Newton. It's clear that Leibniz was much more clear than Newton, because even the language that he used has been preserved till now. The same symbols that Leibniz used have been preserved. And so Leibniz did already, but I'm talking about Newton, this is not that I am diminishing the contribution of Leibniz. But in order just to see this transition, the introduction of infinitesimal calculus into science, the knowledge of the world, and this was an impressive step. Because the uses of infinitesimal calculus, I don't have to, I just point it out because you know this perfectly well, the uses of differential equations. Okay, now this can help us in order to see, well, we have this gravitation, this law, Newton's law, that is universal gravitation, and this is useful to many scales. This law is useful to many scales. Now, does this mean that we understand the universe? The fact that we have such a simple law, does this mean that we understand the universe? That we understand? Maybe this is why I said before that this word is maybe too much. We should, and we say it now, scientists, we say it in this way now. We just describe. We have a very simple model, enormously simple model, even if there were extraterrestrial civilizations having nothing to do with us. This is, by many, is considered the way of dealing with them. This other civilization in some way has to have arrived to such law, in some way, in some way, expressed in different terms, in other, but it must be common. It's so simple. It does not mean that we understand, but that we describe very simply the universe. That we have a model, if you want. Don't say we understand, because philosophers, the other day I was dealing with some conference in philosophy, and they, of course, understand is a lot, understand. But in any case, well, now we go to Einstein, with his equations of special relativity and general relativity. And when Einstein derived this equation of general relativity, at Einstein's time, it was thought that the universe was very small. It was reduced to the Milky Way. It was reduced to the Milky Way at Einstein's time. And also, it was thought that the universe was static. The universe was static. Not that nothing moved, but things moved around, but from the past infinity, from always, from the past to the future, all things would be moving in the same way. It was a static universe. And it turned out that when he derived this law, they did not have as solution the static universe, because the universe would collapse by the effect of gravity. And so he introduced this cosmological constant term. Of course, well, I am not dealing with these equations are extraordinary in the sense that in special relativity he proved that energy and mass were the same thing, two manifestations of the same thing. and this was proven by atomic power, you know, that you can convert energy into mass and mass into energy. Yeah, they were the same thing. And here even more, yeah, that mathematics and physics were the same thing. This is the equation that unifies the two. So the system, yeah, the system is affected already by the masses of the universe. You know, so the measure, yeah, the metric tensor comes from the mass distribution of the universe, incorporating Mach's ideas, the ideas of Ernst Mach to some extent, not completely, but to some extent. But it turned out that, you know, that the universe would collapse, and so he put this term that you can put it here or there because this is just a constant. So is this energy, or is this just reference system? Yeah, it's what it is. Nobody knew. He didn't knew. Yeah, but putting this term that produced a repulsive effect, he could compensate for the attraction of gravity and have a static universe. Yeah. And so he was, well, you know, this is what we have. He was not pleased completely, but this is what we have here. Because, as I say, the universe was static, but lambda was non-physical. He was not quite satisfied. This I have said already, that the universe was the Milky Way plus some nebula. But these nebula were thought to be in the Milky Way. Yeah. Ptolemy, in 150, the year 150, already mentions 5 nebula. The Persian, Arabic, and Chinese astronomers found more. Edmund Halley reported 6 in 1715, Messier 103. So these nebula were appearing. And William and Caroline Herschel published 3 catalogs with a total of 2,500 nebula. 2,500 nebula, a lot of them. Yeah, but those nebula, nobody knew what they were. Well, they were supposed to be, you know, gas distributions. But why? The point was that, as astronomers know perfectly, the measurement of distances is a very, very difficult thing. Maybe one of the most difficult things in astronomy is the measurement of distances to situate objects, yeah, in the universe. This is very difficult. Yeah. And this was done by Hubble in 22-24, so that the Andromeda Nebula was far beyond the Milky Way. And how he did that? He did that thanks to Henrietta Leavitt. Henrietta Leavitt was a distinguished member of what was called at that time at Pickering's Harvard Harem. What is that, Harvard Harem? Henrietta Leavitt, he discovered in 1912, published at Pickering's, the period-luminosity relationship in Cepheid variable stars. These variable stars, they exhibit, yeah, a periodic, the luminosity changes periodically. And the period is related with the intrinsic luminosity of the star, with the real luminosity of the star. And this is Leavitt's law, yeah, is Leavitt's law. And well, of the same time is this Hertzsprung-Russell diagram. I won't describe this because I don't have time. But now the harem, yeah, here, because in another conference with the Russian team some couple of weeks ago, I talked about this harem, and now I decided to present the harem here. Yeah. Here is the at Pickering's Harvard Harem in 1913, also called Harvard computers, because before the existence of these computers, before the existence of computers, these ladies were the computers. And what they were computing, they just were analyzing, photographic plates of the sky, looking for positions and looking for luminosity of celestial objects. This is what they were doing, and they were crucial in the discovery by Hubble, that Andromeda was far away from our Milky Way, some 7 or 8 times more distant than the radius of our Milky Way, and also in the discovery a bit later, some years later, of Hubble's law. Okay, let's continue with the description of Einstein's equations. Carl Schwarzschild discovered a solution just a few months before the formulation by Einstein of his. But this is very famous because it describes the black hole. The Zeta found a solution which corresponds to the maximally symmetric vacuum solution of Einstein's equation in 1917. And Alexander Friedman found another solution. And they say, Alexander Friedman found the expanding universe solution in 1922. Well, what Alexander Friedman found is just a solution of Einstein's equation. A solution of Einstein's equation, nothing more, nothing less. But not, he never considered that this described an expanding universe. Friedman never in his life considered that. He just found a solution, mathematical solution, perfect. And when he sent this solution to Einstein, Einstein disagreed. And Einstein thought, for several years, that Friedman had committed some mistake, that there was a mistake in Friedman's solution, that was not a solution of his equations. This was the idea of Einstein. Now, it was Georges Lemaitre, who already was doctor in Belgium, but he was at MIT from 1923 to 1925, I think. In 1925, this is sure, he submitted a PhD thesis at MIT. It was his second PhD thesis. And during this time, before 1925, while he was in America, Lemaitre visited Bestos Liefers, who before Hubble, some years before, because Bestos Liefers published his first papers in 1912 already with redshifts, and Bestos Liefers presented his results in 1912 in a meeting, a famous meeting of the American Astronomical Society. And it has been recorded that even his intervention was, it was applauded. It was really good intervention. But they had no idea of the redshifts, where they come from. There was a redshift, but what was that? It was attributed also to some atomic processes. As in the case of the Cepheid stars, it's atomic processes, it's the changing from the helium with the ionization of helium, from when it's once ionized or it's double ionized, then the luminosity changes, and this makes the stars variable. So this was also attributed to some atomic processes or something that happened there. It was not clear. Also, Lemaitre found the same solution in his thesis. He found again Friedman's solution, because he did not know about Friedman's work. And he found again the same solution as Friedman. But Lemaitre went much further. Lemaitre also visited Hubble in Mount Wilson. He visited Hubble, and he knew about this redshift of distant galaxies. And so it was Lemaitre. It is recognized that it was Lemaitre the first to formulate Hubble's law, because from this preliminary information, he already saw this proportionality of the redshift with the distance of the galaxies. with the distance of these objects, yeah, already. And also, he showed that he could interpret the solution of Einstein's equations he had found as describing an expansion of the universe. It's very different to say that the object is moving or to say that the object is static. The object is not moving, is in the space-time, and it is the space-time itself what is moving. This is an enormous difference, you know. And the regular movements of distant objects, Lemaitre understood that it was far more simple to attribute them not to movements of the objects themselves, but to movement of space, the movement of the universe, the movement of the universe. The objects were there, and it was the universe what was moving. This is a very profound concept. It's very profound. Lemaitre finished his work, even he finished his thesis in 1925. His real complete work he finished in 1927. And he went to Einstein in a conference in Belgium, yeah, and he presented to Einstein his results. And he said to him, you see, your equations without the need, because this I didn't remark, but this is without cosmological constant. Your equations without the cosmology, you don't need the cosmological constant. Your equations describe an expanding universe. But observational evidence also can be interpreted easily, saying that the universe is expanding. Not that these galaxies are moving there, no, that the universe is expanding. Because it's so regular, it's so proportional, and he understood this and told Einstein about this. And Einstein's answer was the following. He said, you know, well, after looking at his work, Einstein said, well, I don't see any mistake in your calculations, but you know, the interpretation you make of it, your physical insight is abominable. This is what Einstein said, yeah, to Lemaitre. And it took Einstein more than 2 years to understand what Lemaitre was telling him, to realize that yes, the universe was expanding. The universe was expanding. Yeah. So it's a really difficult concept. You know, now we assume that, and now the last thing is that not only expanding but accelerating, because we should understand that. Well, it's easy to understand that the static universe is not a solution of Einstein's equations, because yeah, in the end, because of the gravity force, everything will fall down. But imagine that the Earth was not so big, and we have a stone, and we throw this stone, yeah, we have some impulse, we throw this stone. If the Earth was as small as a mountain, this stone would never come back, You know, this is a solution. Yeah, an expanding universe is a solution of Einstein's equation, is a solution, yeah, because it's an initial condition. The initial condition, as was seen after, is the Big Bang, you know. Yeah, and then, it never come back, or yes, it depends on how big is the Earth. Yeah? So in cosmology until 20 years ago, the main question was, what was the energy density of the universe? What was the energy density of the universe? If the energy density of the universe, it was more than a critical value, then, you know, even if now the universe is expanding, yeah, it will then contract. You know, it will expand, but now it will contract. But if the energy density of the universe is less than this critical value, then the universe will continue expanding forever. And this was the big question, you know, that how is it no, because it was distinct. Okay. Now, the Big Bang theory Yeah, it was not proposed, this name, this name was not proposed by Lemaitre, because, of course, going back in time, if the universe was expanding, already Lemaitre understood that going back in time, it should have been very much concentrated in the past, very much concentrated. Yeah? But it was Fred Hoyle, Hoyle, Gould, and Bondi proposed an alternative theory. And in this famous BBC radio forecasting in 1949, in trying to diminish Lemaitre's theory, Fred Hoyle said that in Lemaitre's theory you needed this impulse, what I said with the stone, you need to throw it, and this at cosmological scale would mean an enormous big bang, so saying this is impossible, this is ridiculous. He didn't say it was ridiculous, he just said big bang, He didn't say it was ridiculous, but it was disrespectful. It was in this disrespectful way, because Hoyle, Gould, and Bondi had another theory, which was the steady state theory, where the creation, it was matter creation in the universe in order to preserve energy conservation, but it was thanks to a C field. In some way, they say this is a precursor of inflationary theories, using the fact that the energy corresponding to the gravitational potential is negative. Is the same principle that is used in inflationary theories. You can create matter and energy, ordinary matter and energy, through creating at the same time this gravitational field at the expenses of the gravitational field that has a negative energy. So you have at cost zero, free lunch, as Vilenkin and collaborators say, a free lunch, you can have this creation without violating the energy conservation principle. This was already anticipated in this theory, and this theory did not need a Big Bang. Well, then the Big Bang was discovered, and so I won't talk about that. But I won't talk about that. But in fact, it was discovered. I just jump now to recent observations, where now we have discovered that the expansion of the universe not only expands, the expansion is accelerates, the expansion accelerates. So it's no more the stone, it's no more an initial condition. This stone must have a motor, it must accelerate. And now the big question is, what accelerates the expansion of the universe? What can accelerate this expansion? For this we need a force, again, going back to Galileo and Newton.
Excuse me, do you mean that there are solutions to the Einstein equations that can be interpreted this way?
Accelerating? No. You need, again, the cosmological constant. If you go to Einstein's equations, of course, you have to reintroduce the cosmological constant in order to provide for this acceleration. But now, in times of Einstein, it had no meaning. So this cosmological constant had no physical meaning. Now, at least we can attribute a meaning to the cosmological constant, which is the quantum vacuum fluctuations. The fluctuations of the quantum vacuum exist. They cannot be suppressed because they are allowed by Heisenberg's uncertainty principle. Heisenberg's uncertainty principle says that the minimum energy state of a quantum system, the minimum energy state of a quantum system cannot be determined with absolute precision. You have fluctuations there which are of the order of Planck's constant. And this seems very small. But when you calculate this, this is the next transparency, it can be very big. Yeah? But now, before I come to that point, in Einstein's equation, these vacuum fluctuations which are here, those are the fluctuations of the quantum vacuum. Yeah? They go together with the cosmological constant term. You know, they go together. So even if you don't have this term, you say, well, what is lambda? What is lambda again? Well, maybe there is no constant term, but these vacuum fluctuations are there, provided that these vacuum fluctuations are a form of ordinary energy. You know, that this is an energy that has to be counted, because, you know, in Einstein's equation, you have to count all forms of energy of the universe. You put to the right-hand side, all forms of energy, all. Yeah, but now the question is vacuum fluctuations, which are virtual fluctuations, is this an ordinary form of energy or not? Has this to be counted in Einstein's equation on the right-hand side? If they have to be counted, they come here, you know, and they produce the effect of a cosmological constant. So, and this is the only known explanation, you know, in Einsteinian physics of the acceleration of the universe that could be reasonable, you know, through vacuum fluctuations. Vacuum fluctuations. But now the problem is that is the cosmological constant problem. The problem is that when you calculate this thing, the number is too big. Well, actually, well, this is again the same. Actually, this gives infinite. This gives infinite because if unrestricted, there are fluctuations of any kind, of any frequency. Corresponding to any frequency, there are quantum fluctuations. So this sum is infinite, Now you start to argue, and Pauli already in the 20s understood this thing, and he did some computation. And at Pauli's time, a reasonable regulator, so to say, of course, but infinite frequency, this has no physical sense, you know, physically, you know, infinite, what is infinite? It will be up to some point, yeah, there will be frequencies up to some point. And he put as what is called in physics cutoff, it's called cutoff, he put as regulator, as cutoff, he put the radius of the electron, electron radius, because this seemed to him reasonable in the 20s, yeah, and doing this, he calculated and he could see that these vacuum fluctuations would be even then so powerful, this gives such a big number, that the radius of the universe did not reach to the moon. And this is what he said there. Yeah? Would not reach to the moon. Nowadays, other regulator, we put here a different regulator, which is the Planck length. Why the Planck length? Because modern physics, modern quantum field theory is thought to be valid, you know, until the Planck length, but not beyond. Yeah, so quantum field theory is not believed to be valid beyond the Planck length. Beyond the Planck length, nobody knows. So we put as regulator the Planck length. And putting the Planck length, then we obtain this number that appears in the press, you know, that we have 123 orders of magnitude difference between the calculation of these vacuum fluctuations and the real acceleration of the universe observed, you know, by astronomers. So this is the problem of the cosmological constant. An enormous problem, the biggest problem in the history of physics, because never in the history of physics there have been a discrepancy of more than 100 orders of magnitude between observation and calculation. This is a problem, but this is the only thing. And well, I will have to finish at some point. I won't explain about this because here is just what I said. Yeah, and well, about the point, if these vacuum fluctuations are to be considered as an ordinary form of energy or not. You know, this is not a trivial question, and there have been some calculations, and in different coordinate systems, in particular in Fermi coordinate systems and in Rintel coordinates, and the result is positive. The result in these systems is positive, in the sense that yes, they have to be counted. They are ordinary forms of energy, yeah, but still missing is a gauge invariant procedure in order to calculate this. You know, so this is very difficult to answer. But in reasonable coordinate systems, it has been answered in the affirmative. It seems that these vacuum fluctuations, they contribute, yeah, in the normal way to the energy balance of the system. I don't have time in order to go to my specialty, which is the zeta functions. But I want to say some couple of things more. The one is this. Yeah, no, here I just provided the connection with the zeta function, but maybe I can just say this. Well, by passing, you know, that in calculating these vacuum fluctuations, the Riemann zeta function, the use of the Riemann zeta function as an analytical continuation method to regulate infinite series, you know, to provide values to infinite series is very useful. And this is called the zeta function method, which is my specialty, you know, in this I am rather well known. Yeah? But this is just a use of this zeta function. Yeah? And here is a bit of the history of this whole development, starting from the Riemann zeta function. Hardy and Littlewood already they in this book, in this famous book by Hardy, Divergent Series, yeah, they already explain how the zeta function can be used as a way to give sense to infinite series. You know, let me. Let me just put this rather simple example. No, we have 1 plus 2 plus 3 plus 4, and this is infinite. You know, this is infinite. Yeah. But if we interpret this, yeah, no, but those were the frequencies of some quantum system, and this is just the value of the zeta function n to 1. But this is n to 1, this is the Riemann zeta function for s equal to -1. Analytically continued, you know, because this is only valid, you know, in the Riemann zeta function, this series expression is only valid here, but it can be uniquely continued as a meromorphic function to the rest of the complex plane with only one pole here, yeah? and then you say, well, analytically continue this, and what we obtain is -1 over 12. And this may seem crazy. You say, okay, yes, this is mathematics, but has this anything to do with physics? And then you go to a physical system. You go to a physical system for the Casimir effect configuration, which is fluctuations of the quantum vacuum, and the answer is yes. It seems that nature behaves in this way. Crazy, because you know the process of analytical continuation is very nonlinear. You have no intuition. You have no intuition of the result in relation with the series. You have no intuition. But nature, it seems that nature makes use of this analytical continuation, because you go there with these numbers and then you obtain results, reasonable results. Okay, this method was developed starting with Hardy and then Lemaitre, and this was a bit of this history, and silly in the complex power of elliptic operators, because this is is very useful in physics, because in physics what you have is sometimes not just differential operators, but you have powers of differential operators which are no more differential operators but pseudo-differential operators, and this is the silly calculus. And then it was further continued by Ray and Singer, who, you can express not just the Riemann zeta function with the integers, but the zeta function corresponding to a pseudo-differential operator as this trace of the operator to the power minus s. This is a formal expression, but it can be given sense by analytical continuation. And this, under very general condition, these zeta functions for pseudo-differential operator exist. And then you can obtain determinants, and this is the ordinary way in which these determinants are obtained. For instance, in the Atiyah-Singer formula, the famous Atiyah-Singer theory, and there, this is the ordinary calculus there. So this is the calculus that is very useful for these calculations. This is the calculus that is very useful, and in physics, the persons who introduced this methodology were Stuart Dowker and Raymond Critchley in 1976, and Stephen Hawking in 1977 in a couple of papers. Well, the first one has about 600 citations, and this one has 1100 citations or so. That for rather mathematically oriented papers is a lot of citations. Those were the first to introduce completely, properly, a method of making sense of these infinites as the ones that appear in these vacuum fluctuations, as I have said before. These infinities are regulated very beautifully in this way, through these zeta functions of the corresponding Hamiltonian operators. Okay, and now one point which is important is the following, because these vacuum fluctuations, most of the time they don't accelerate the universe. On the contrary, they contract it even further. They have the wrong sign. And this that they have the wrong sign is due, well, I don't have much time to go, but I will summarize. This is an important principle in quantum field theory, which is reflection positivity. Is Osterwalder-Schroeder theory of 73-75. This is very important. This is a very important principle in quantum field theory, which says simply that opposites attract. Opposites will always attract. Opposite will always attract. And this translated to these vacuum fluctuations and to the Casimir effect, when you put the two plates, is that they will always attract, not repel. But this can be avoided, this is the point. This can be avoided, when you consider mirror probes in a Fermi sea. Electron gas fluctuations become important when you put periodic boundary conditions for fermions, and when you put Robin boundary conditions in general. And those conditions in some systems, now I am jumping, because this is not logical as the first part that I described. Those are just calculations with the vacuum fluctuations in order to make sense of them as possibilities for explaining the acceleration of the universe. This is just the point, but I am jumping here. But summarizing, there are situations in which, considering brane walls with large extra dimensions, there are situations which are not so unreasonable. So those are the situations that are considered in some string theory, in some string theories, and in some brane wall theories. Those are situations that are ordinary there. There are situations in which you can found contributions of these vacuum fluctuations which are of the order of magnitude needed to explain the acceleration of the universe. But this is not the final answer. This is just some contributions. You still have the big problem of the cosmological constant. Those are some exceptional cases in some way, you know. But and if you don't have this, and with this I will finish. Well, I will go quickly through this discovery, yeah, of the fact that you know, the two teams of Ries, Schmidt et al. And Perlmutter et al. In this team, there is a researcher from Barcelona University, Pilar Ruiz Lapuente, who the last week she was in the Nobel, yeah, it was in Sweden, yeah, in the Nobel Prize. She was there, yeah, because she is one of the signers. Each team has about 30 researchers, each team, yeah, and this Pilar was one in this. And these three got the Nobel Prize, yeah, and they just were looking for the deceleration of the universe expansion. The deceleration, because as is explained in this transparency here, this comes from Einstein's equations. You know, these Friedmann equations come just from the Einstein's equation. As I said, through the Friedmann solutions for an homogeneous and isotropic universe, which has been proved to be to a great precision. Yeah. What you obtain is deceleration. What you obtain is deceleration there. What you obtain is deceleration. And these two teams, they were just looking for the deceleration of the universe. But they saw that the universe was accelerating, was not decelerating, but accelerating. Even if they were looking for deceleration. And this is the mystery. What accelerates the universe expansion? What accelerates the universe expansion? Well, I have presented one possibility, which is the vacuum fluctuations, but is not in good shape, yeah, to say the least, because there is the big problem of the cosmological constant. It's not in good shape, but is the only one if you just restrict to Einsteinian theory. Now, the other possibility is to go beyond, to say, you know, well, Einstein has been valid until this point, but, you know, it cannot describe the whole of the universe. So we put here extra contributions. We put here extra contributions here. And those are called FR theories, and there are other theories which extra fields, which in some way are equivalent, more or less, well, not quite equivalent, but rather equivalent to these FR theories, in which you just put more powers, in a way, powers of R in Einstein's equations. This is the other possibility in which we are working. And without giving more details about that, I will finish here, because I think my time is over. So.
Concerning the intelligibility of the universe, what is extraordinary is that we can imagine in the future the astronomers trying to reconstruct once more the story of the universe when the galaxies will be far enough that we will not be able to see them. So at this epoch, the universe will be formed just by one galaxy.
Again.
Our galaxy. So what they are going to see is just a static universe, I was assumed before Hubble. So the question is that we are a very special moment where we can understand the universe as it is.
Yeah.
This it looks extraordinary.
Yes. Yeah. No, this is a thing that requires explanation, even this point. Yeah. Why we are living in this special moment? This is one. Yeah. This is a point that requires explanation. Yeah. And also, even without invoking these late times, nowadays there are theories because it's very difficult. From the beginning, I didn't talk about how you can originate, when you can make this Big Bang happen, and you can originate the universe, create the universe. It's very difficult, if not to say impossible, it's reasonably impossible to create one universe as ours, just one. It's much more easy to create many universes, in all these kind of fundamental theories. In this kind of fundamental theories, it's easier because then you create, and ours is just one among an infinity of universes, among an infinity of possibilities. This is much easier. So to say that even now, there are many cosmologists. The other day, García Bellido, in a TV program, he said that most of cosmologists think that there are many universes, that ours is one. Well, this is an opinion. Of course, there are many cosmologists. There are some cosmologists, or many, if you want, who, because of this that they think that we are just in one of many universes.
It's more comfortable. I have just another question. Sorry. In one of your, you have shown that the energy of the vacuum is of the order of milli-electron-volts.
Mm-hmm.
And at the same time, when you are trying to make the summation of a series of fundamental nodes, taking into account that fermions contribute negatively and bosons contribute positively, when you look where you have to cut, you are only once more at the scale of the milli-electron volts. And so this cannot be a causality. Why? What is the physics at this scale?
I don't know. I don't know if there is any. I don't know if there is any special physics there. I don't know. Of course, there are different arguments, to put other cutoffs and to deal in a different way with this, but and we also have some systems in some ways where you have reasonable things, but you have to convince the others that this is the natural situation, that this is the natural thing to do, not just some possibility or some way, because there are different approaches that got the right number, but none of them is convincing, so to say. Aquí.
Just a small question. Can you point in the sky where the Big Bang took place?
Where the Big Bang took place? Everywhere. No, for this you have to understand how is the universe. The universe is homogeneous and isotropic and democratic, completely democratic.
The Big Bang is not in this universe.
The Big Bang is in this universe, but for this one has to imagine, this is what I explained recently in a TV program, that you have to explain, to make an idea of how the universe is. The universe is not a ball.
No, it's a sphere.
It's not a sphere. No. It's a sphere surface. Is a three-dimensional sphere surface.
For a mathematician,
a three-dimensional sphere. Okay. Yes, that's it. That's it. And then what do you point? The past. This sphere is just one point, and so it was everywhere. It was everywhere.
At the center of this sphere.
Yes, which is the universe in the past.
In our universe.
No, is in our universe in the past time, because the radius is the time coordinate. The radius of the radius of this ball is the time coordinate.
But our universe is just a sphere.
Yes.
So the Big Bang is not there.
The Big Bang is everywhere now.
All right.
We can feel it, and if you go back in time, this sphere was smaller.
All right, we will go back in time.
Yes.
But, I think we agree.
Yes, you know. Then it was one point. Now it's everywhere. We feel this everywhere in the same way.
So the universe at this moment, in your way, is a three-dimensional sphere, empty, where that has inflated from the...
Yes, yes. That's right. That's right.
Good enough.
Yeah.
We have another question here.
I'd like to ask you, what is it, in general, vacuum fluctuation, how it can be connected with acceleration of expansions of the universe? Because fluctuation word means not, how to say, chosen direction. And if our universe is expanding in general sense, that you already have some direction of the process. And fluctuation means that you haven't. Because
yes. You can fluctuate. You have some direction, but you can fluctuate quantically.
And in general, what is it? Vacuum fluctuation?
Is a quantum.
Some words.
Is a quantum process. Well, though this has been measured in this so-called Casimir effect.
No, please, without names, the process. What actually, what from this the consequence?
What?
The process.
Physical process.
Yes.
You have two plates in the vacuum, and they attract.
Yes, and how it acts to the universe to expand.
How it acts to the universe? Because it's a form of energy, and you have to count them as other forms of energy. This is what I said. This is not 100% clear. You may be right that this has not to be put in Einstein's equation. This I was explaining. This is not to be taken for granted that you have to put there. Yeah, for this they have done these calculations, specific calculations with some specific models in some specific coordinate systems, where counting these vacuum fluctuations is a part of the whole process. And this was done in Casimir effect things. Yeah, that this coupling had to be counted, because if not, you know, the equation was not closed. So this has been proven, yeah, by Fulling. Yeah, Fulling is a great specialist in that. You know, very reasonable person, very well known and famous. Yeah, and they did this. It's not completely clear, but in some cases it's clear. It's clear that they should be counted there. Yes.
Okay, is there some other question? Well, otherwise, let's thank the speaker again for the wonderful.